All right, so today we're going to do a lot of the same theorems we've already done, okay, except we're going to apply them to complex numbers. Okay, so I'm going to go over complex numbers really quick that you would have done in like Algebra 2, how you add them, subtract them, and then I'm going to get right into what we're really going to use complex numbers for. Okay, so remember this idea, we've already had it, that if something is a root of a function, when you plug it in, you get 0. Okay? It also means it's an x-intercept. Okay, I think we've written this concept at least 4 separate times now. So you already have that on your list of notes, I think, from Monday. Equivalent statements about roots. Okay, if a polynomial does not cross the x-axis, then there are no real zeros. Okay, try to graph the parabola x squared plus 5. It won't cross the x-axis. It doesn't mean that there aren't roots. It means that there are no real roots. And actually, here's another example. Parabola x squared plus 1. Okay, if you graph that, it's a parabola that's been shifted up 1 unit. So it's pretty clear it never crosses the x-axis. Which means if you try to solve it, there are no real roots. Okay, maybe if we have a little time, we'll come back to that and we'll solve that. And we'll find what the roots are. Any question on that idea? When something does not have real roots? Yep.
So if there's no real roots, is there like a imaginary
Yes.
axis?
Yep, there's imaginary answers.
But is there like an invisible x-axis that we don't?
So, on the graphing calculator, we can't actually see imaginary roots. Yeah. We will graph things using a complex and real axis, but that's a little different. So there's really no way to visualize imaginary roots using what we're using. So we're just going to have to find them algebraically. That's the only way to find them. Okay, so here's a basic definition. Okay, I is the square root of -1. Okay, that's not something we prove. It's a definition that we build off of. It's just the way it is. I is the square root of -1. So what would I squared be? Yep. -1. Right, so what I want to do is I want to plug I into the previous equation and see what happens. So I get y equals, plug in I, square it, and plus 1. What did we just say I squared was? It's -1. -1 plus 1 gives me 0. So guess what? I is one of the roots of x squared plus 1. And the other, anybody know what the other root is? I and yeah? Negative I. Yep. Negative I. If you plug in negative I and you square it, a negative squared is a positive, so that basically cancels out, and now you're back to what we just had. I squared is -1 plus 1 equals 0. Okay, so negative I times negative I is positive I squared. So those are your two roots in that equation, I and negative I.
So is negative I positive?
Is what?
Negative I positive?
Is negative I, well, negative I would just be the negative square root of -1. We don't really use, we won't really mention that very much.
Okay.
We generally write the square root of -1 as just I. Yep. And if you needed negative I, you just write negative I, but we won't be using the negative square root of -1. That's just a little awkward to say. So a complex number basically has two parts. Okay, it's got a real part and an imaginary part. Okay, your real part I'm representing here is A. The imaginary part is just the B. Okay, it's the number, it's the coefficient basically of I. Okay, we treat I like a letter a lot of times when we're doing complex arithmetic. Even though it's a number, we can treat it like a letter, and it helps, like combining like terms and things like that makes sense. So here's some examples of complex numbers. Okay, 3i, negative 7i. These two are special because they're called pure imaginary numbers. 3i and negative 7i don't have any real parts to them. You could think of the real part as 0 plus 3i. There's no real part. It's just 3i. Okay, 4 is also a complex number. Kind of the opposite, though. It has no imaginary part. 4 plus no imaginary parts, 0i. We generally, if a part is 0, we don't write it. Here's a complex number that has both a real and imaginary part. Real part's 2, imaginary part 3. And here's another complex number, 2/5 minus I. Or you could write 2/5 minus 1i. Okay, just like when you have variables, we generally don't put the coefficient if it's a 1. Okay. If you want to put in a 1 right here, you could. So two complex numbers are equal to each other only if the real parts and imaginary parts match. So 3 plus 2i is the same as 3 plus 2i. If you had 3 plus 2i and 3 minus 2i, those aren't the same. Even though the real parts are, the imaginary parts are not. Okay, so real parts and imaginary parts have to match. Okay, when we do arithmetic, we can treat I as a letter. Okay, I want you to remember that it's not a letter, though. It's the square root of negative 1. But it kind of helps, so if you get something like 2i plus 5i, you could write it as 7i. Same way you'd do it if it was 2x plus 5x. You write 7x. Okay, when we have to multiply complex numbers, especially complex numbers that have both a real and imaginary part, it's like the distributive or double distributive property. Some people use FOIL. You remember that? When we divide complex numbers, we're going to have to use the idea of a conjugate. So we'll talk about that. And then for square roots. Right, if you have to take the square root of a negative number. Okay, up until now, we've said that you can't do that because you don't get a real answer. Well, you can. You're going to get a complex answer. So first thing I've done under the root is I factored it as negative 1 times x. Right? So negative 1 times x, that's still negative x. And then once you have a factor as your radicand, you can separate it into two roots. So the square root of negative 1, separate, and then the square root of x, separate. And then earlier we talked about the square root of negative 1. What did we say that was defined to be? Michael? I. So we got I. So we have I times the square root of x. So the basic idea is that if you read a negative under a square root, when you take the square root, it comes out as an I. And then you just have a number under the root. All the properties about reducing square roots, everything like that still applies. All right, so let's try a couple with taking negative square roots. Okay, what would the square root of negative 4 be? The square root of negative 4 would be, yeah?
Negative 1 times 2 times 2.
Well, it's going to have I in it, because anytime you take the square root of a negative, it's imaginary or complex. Yeah? 2i. Okay? Generally, when you have a root involved, we put the I in the front, because if you put the I after it, it looks confusing. Is that I supposed to be under the root, or is it outside the root? So when the answer, especially for these two on the right, you're not going to be able to take the square root of 7 or 20 and get a nice answer. So we're definitely going to want to leave the I in front. But here, we can take the square root of, we could write it like that, I times 2. And that's basically how the format is up here. But when we can simplify it, and it's a perfect square, we put the I at the end, 2I. Okay. How about the square root of negative 7? What would that one be, Orlando?
I square root of 7.
Yeah, there we put the I in front, so there's no confusion about the I being under the root. Yep. And I can't simplify the square root of 7, so that's why we do it that way. How about square root of negative 9? But Nick, what would the square root of negative 9 be?
3i.
Yep. And if you get stuck, you can always go back to the process I explained, break it up. It's the square root of negative 1 times the square root of positive 9. Square root of negative 1 is I. Square root of 9 is 3. And then just write it how we conventionally do. I times 3 is 3i. And how about this one? The square root of negative 20. Yep.
2i times the square root of 5.
Right, can you explain what your first step would be, how you got that?
I see it as negative 1 times 20 inside the box.
Okay, so you could split it up like that. Square root of negative 1 times square root of 20.
Square root of negative 1 is I.
Okay.
Square root of 20 is 2 times square root of 5.
Right. You got to split up that square root of 20 as square root 4 times square root 5. And then we get I times 2 times square root of 5. And then it was switched perfect. Instead of I times 2, write it as 2I. Any question on those steps to do the square root of negative 20? All right. So let's try addition. Okay, so we're going to add two complex numbers. Okay, when you add complex numbers, okay, I'm assuming you've already done this in algebra before this. We just combine like terms. Combine the real parts, then combine the imaginary parts. Okay, so when I get my final answer, what would the real part of my final answer be? Just the real part, yep. Yep, 7 and 4 gives me 11. And what would my imaginary part be? Oh, Hassan? Yep, 2 and then I. So the imaginary part itself is just the 2, exactly what she said. And we put the I there so you know the 2 is imaginary. So that's how you add complex numbers. Subtract is very similar. Except you have to remember there's like a distributive property happening there with the negative. So it's a minus 6 and a minus I. Okay, Brandon, what would be my real part here? Yep, negative 2. And my imaginary part is going to be negative 2I minus I. Okay, Brian, what's negative 2I minus 1I?
Negative 3i.
Yep, negative 3I. Okay, so there's adding and subtracting. Okay, multiplying. What did I say this was similar to? What technique do some people use to remember how to do this?
Foil.
Yeah, FOIL or double distributive. That's exactly how you're going to do it. Okay, remember that your final answer, all the i's to the first power, should be combined as a single term. And you should not have any I squareds in your final answer, because we said I squared earlier was something, right? So, Tahina, what would be my first multiplication I would do here?
2 times 5.
Good, 2 times 5. Okay. Michael, my next one?
2 times negative I.
2 times negative I. It's a negative 2I. Okay. Shannon, what would I do next? 3i times 5. So that gives me a plus 15i. And the last one, how about Taylor?
3 times negative I. Or
3i times negative I. Right, so let's look at it. We have a positive times a negative, which is going to be a negative. So we take care of the sign. And now we have 3i times I. What's 3i times I? Yep.
3i
3i squared. Okay, a couple things we have to do to simplify. Combine your like terms. Okay, negative 2i plus 15i. Josh, what will that be? 13i. And what about negative 3i squared? What happens there? Mm-hmm.
So negative 3, it's just negative 3, but I squared is negative 1. So negative 3 times negative 1 is 3. So you're left with positive 3.
Right. So what's going to happen here? You get that negative 3 times negative 1. That's a positive 3. Positive 3 can now be combined with positive 10. And we get 13 plus 13i. That's just a coincidence that the real part and imaginary part came out the same. It usually doesn't happen. Okay. Any question on how we simplified that I squared? All right. And the last type we have to do is division. But before we can look at division, we have to understand the idea of a conjugate. Okay, a conjugate, when we're talking about a complex number, is when you change the sign of the imaginary part. Or the verb we use for that is negate. You negate the imaginary part. So if I had 3 plus 2i as my complex number, anybody think they know what the conjugate of 3 plus 2i would be? Nick? 3 minus 2i. Yeah, you just change the sign of the imaginary part. Don't do anything to the real part. How about if it was 4 minus 5i? What would be the conjugate of 4 minus 5i? Yep.
4 plus 5i.
4 plus 5i. Good. How about 3i? What would be the conjugate of 3i? Orlando?
It'd be negative 3i.
Yep, negative 3i. And the last one, 6. What do you think the conjugate of 6 would be? Yep, Brandon. Stays the same, 6. So the last one, if you're confused, think of 6 as 6 plus 0i. There's no imaginary part. The conjugate would be 6 minus 0i. Well, plus 0 and minus 0, it's the same thing. Okay. So when we want to divide two complex numbers, what you do is you multiply the top and the bottom by the conjugate of what's in the bottom. And the reason why we do that is, well, when we FOIL conjugates together, something special is going to happen. Anybody know what happens when you FOIL two complex numbers together or distribute them that are conjugates? Right, so let's see what happens then. Okay, so we have 5 plus I divided by 2 minus 3i. So we need to multiply the top and the bottom by the conjugate of what's in the bottom. Okay, what's the conjugate that I'm going to use here? Mm-hmm. 2 plus 3i. Good. Okay. Let's FOIL out the top first. So we're going to get 5 times 2 is 10. 5 times 3i is 15i plus a 2i. And then I times 3i. Why don't we simplify that as we write it down? What's I times 3i fully simplified? Mm-hmm. Negative 3. Okay, it would be 3i squared, but then I squared is negative 1. So 3 times negative 1 is negative 3. And now let's do it in the bottom. You have 2 times 2, which gives me 4. What's 2 times 3i? 6i, yeah. And what's 2 times negative 3i? Negative 6i. Okay. We'll look at that in a second. And now we have negative 3i times positive 3i. All right, so I'll do this one in 2 steps. So it's negative times positive. That's a negative. 3 times 3 is 9, I squared. Okay, let's simplify the top. What's my final answer in the top?
7 plus 17i.
So we get 10 minus 3 is 7 plus 17i. Now in the bottom, a few things are going to happen. Anybody tell me one thing that's going to happen in the bottom? Yep, Silvio.
Negative 9 turns to a positive 9.
Right, I squared is negative 1. So it's going to cancel out that. That's going to become a positive, which now allows me to do 9 plus 4 is 13. And what about the imaginary part in the bottom?
Cancels out.
6i minus 6i is 0i. So there's no imaginary part left in the bottom. Generally, how they write the answer is the real part and imaginary part separate. So they do it like this. Everyone see how I separated that into two fractions? Just put each part over 13 separately. So my real part is 7/13. My imaginary part is 17/13. And that's how you divide complex numbers. Okay, so that's just intended to be a quick review of complex numbers. So now we're going to use that to actually do what's in the section, which is finding roots of polynomials. And now your roots could be real, or they could be imaginary. All right, so let's try to find the roots of this equation. So when you're finding the roots, you're basically letting y equal what number? 0. We're trying to find the x values that would solve this equation. Well, this is a pretty routine kind of equation. We could try to factor it, but that won't work. So what else can we do besides factoring it? And look at the type of equation it is, like the highest exponent. That tells you the type. Oh, yeah, Nick, can you just tell me what kind of equation is it?
Quadratic.
It's quadratic. So how can we solve a quadratic equation that we can't factor? With the quadratic formula. And this is exactly a quadratic equation. It's not even similar to a quadratic. It is a quadratic. So in this case, we just need to make sure we know A, B, and C. Right. So how about Julia? What's A?
1.
Yep. A is 1 and B?
1.
1 and C?
1.
1. That's going to be interesting. So all 1. Let's take a look at what happens. We get B squared minus 4 times A times C. So forgot my negative B part. So negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. Okay, so let's solve it and see what happens. Negative 1 plus or minus the square root of 4 times 1 times 1. That's just 4. So 1 minus 4 gives me a negative 3. What kind of answer am I going to get when I solve this? Yep, it's imaginary. Okay, how do we know it's imaginary?
It's a negative square root.
Yeah, we have a negative square root. So we have negative 1 plus or minus, and somebody tell me what is the square root of negative 3? Just write it with I. Yep, Josh?
I times square root of 3.
Yeah, it's just I root 3. And that's about as much as you can really do. And there's your two answers. Negative 1 plus I root 3 over 2 and negative 1 minus I root 3 over 2. You can use the plus or minus symbol to write both answers together. Again, not something you can graph and find the answers. Graphing will only give you the real roots. There are no real roots in this problem. Okay. Any questions on that? Okay, so that's a quadratic. And if we take a look back at example 4, you notice the roots, they're conjugates. Right? If I write them out separate, it makes it very obvious. It's negative 1/2 plus, you have I root 3 over 2. And you also have negative 1/2 minus I root 3 over 2. Okay, the two answers that we just got are conjugates. And in fact, that always happens. If you know A plus BI is a root, then I guarantee you A minus BI is also a root. Complex roots have to occur in pairs. You can never have a polynomial that has an odd number of complex solutions. They always come in pairs. So you could have 2 complex, 4, 6, 8, but you can't have an odd amount. So if you were solving a polynomial and 5 minus 2i was a solution, I guarantee you 5 plus 2i is also a solution. So it's kind of nice with complex roots. You kind of get 2 for 1 here. So if you find one, you automatically have another one. Okay, everything that we've learned, whether it's the remainder theorem, factor theorem, and synthetic division, which is what we're going to look at now, they all work with complex numbers without changing anything. So what I want to do is show 1 minus 2i is a 0 of that polynomial. Okay, so what I'll do is I'll use synthetic division. 1 minus 2i is going to be on the outside of my symbol, and I'm going to divide that root synthetically into the polynomial and see what we get. Okay, so put 1 minus 2i okay, on the outside. List your coefficients. 4. What do I have to be careful of here when I list my coefficients out? Yep.
You need to remember to include the 3 degree.
Which would be what in this case?
0.
Yeah, your cubic term is going to be 0 because it doesn't exist. We've got a quadratic term, linear term, and constant. Okay, now let's do synthetic division. So bring down my 4. And this part, it can be a little tough to do all the distributive in your head. So if you have trouble with it, you could do it off to the side. But I'm going to do 4 times 1 is 4. And 4 times negative 2i is negative 8i. So when you have to multiply a real number times a complex number, you don't have to use FOIL. It's just a simple distributive property. And that's it. Okay. Now we add these up. 0 plus that gives me 4 minus 8i. All right. And now this is the part where it gets a little tedious. We have to multiply 4 minus 8i times 1 minus 2i. Luckily, we're only going to have to do this a couple times, and then we're done. So 1 minus 2i times 4 minus 8i, and then we're going to write the answer under the 17. Okay, so 1 times 4 gives me 4. I have negative 8 minus 8, so that's negative 16i. Just combining it as I go. And then I have negative 2i times negative 8i. A negative times a negative, that's a positive 16i squared. But then I squared is negative 1. Okay, so when I FOIL that out, I'm going to get 4 minus 16 is negative 12 minus 16i. Okay. If you need to do it out step by step, that's fine. But for the purpose of synthetic division, I just want to show you the remainder should be 0. So get negative 12 minus 16i. Okay, now add it up with the column above it. What's 17? Take away 12. Yeah, 5. All right, and now we're going to multiply 1 minus 2i times 5 minus 16i. Okay, on a test, I probably wouldn't even give you one that had 5 columns in it, maybe at most 4. So you're not going to have to do as many distributive properties. All right, so 1 times 5, we're going to get negative 16 minus 10. Okay, what's negative 16 minus 10? Yep. Negative 26i. And then we're going to get negative 2 times negative 16. That's a positive 32. I squared changes it to a negative 32. Okay, so what's 5 take away 32? Yep. So negative 27 minus 26i. And now combine 14 and what we just wrote. Well, we can just do it out. 14 take away 27 gives me negative 13. Okay, and hopefully if we haven't made a mistake, we're at our last step, and I'm hoping I get negative 65. If I do, then that's going to add up to 0, which is what I want to happen. Let's try it. So we have 1 minus 2i times negative 13 minus 26i. Okay, let's see. So 1 times negative 13, we have 1 times negative 26. But then what's negative 2 times negative 13? That's a positive 26. So the I terms are going to cancel. That's good. And then we're going to get negative 2 times negative 26. How much is negative 2 times negative 26? Positive 52, but then the I squared is going to make it a negative 52. What's negative 13? Take away 52. Good. Negative 65, remainder 0. That's what we wanted. That's the only one we're going to do like that. So we proved that 1 minus 2i is a root using synthetic division.
So on a test, if you gave us that equation, told us to find the zeros, and then we would have, the 1 minus, or whatever, the 1 minus 2i, and we'd have the 1 plus 2i. Could we just say 1 plus or minus 2i?
Yeah, I guarantee, yeah. If 1 minus 2i is a root, 1 plus 2i is a root.
Okay, so we can just do plus or minus.
Yeah, yeah.
Okay.
That's a little different question. I'm not asking you to find the roots
Yeah.
here, but we are going to do one in a minute where I have you find roots. Yeah, but it won't be quite this bad. Okay, so we proved that 1 minus 2i is a root. Okay, so the next thing is this kind of just thinking question. It says odd degree polynomials will always contain at least one real 0. Guaranteed. Every time. You'll always have at least one real 0 if your polynomial is an odd degree. Why? That's not true if it's an even degree. Could be true. Doesn't have to be if it's even. Yeah?
Because imaginary numbers will only come in pairs, so there will be one number left over, and it can't be imaginary and real.
Okay, so yeah, you're guaranteed imaginary numbers come in pairs, so with a cubic, you either could have, if you think of them as real and imaginary, you could have 2 imaginary, and then you'd have to have 1 real. You can't have 1 imaginary, that's impossible. You could have no imaginary and 3 real. That could happen. And then you could also have no imaginary and 2 real with one of them repeated. Or no imaginary and 1 real repeated 3 times. Anybody think of another reason why that would happen graphically? Think about how it looks. Yeah?
Because it's going to go in either direction forever, so eventually it's going to cross the x-axis.
Right. Polynomials are continuous functions. The end behavior, one end goes up, one end goes down. It's got to cross the x-axis somewhere. That's important. Okay, so let's find the zeros of x cubed minus 1. Okay, this one I'm going to take a little shortcut. This is a difference of 2 cubes. Okay, back in Algebra 2, you learned a formula for factoring a difference of 2 cubes. If you don't know that difference, what we'd have to do is use the rational root theorem, we'd have to find a possible rational root. We'd have to graph it, confirm that it's a root, divide through synthetically by it, and then get the quotient. Okay? That would take a lot of extra work. But if you know the shortcut for factoring, x cubed minus 1, okay, factors into x minus 1, and then a quadratic. Again, if you don't know that, it's okay. You'd find 1 as a root. You'd divide through synthetically. In fact, I can do that quick to show you. How would I know 1 is a root? I would use my graphing calculator to check it. And then divide it in. You have 1, no x squareds, no x's, and a minus 1. It's actually a pretty fast synthetic division problem. So we get 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Too many 1s. 0 times 1 is 0 plus 1 is 1. 1 times 1 is 1. Remainder 0 proves it's a root. And then this is my coefficients. 1x squared plus 1x plus 1. That's exactly how I got that. Okay. But if you know the shortcut for factoring, it saves you the time from having to do that. All right, so this part.
What is the shortcut?
The shortcut, if we have time at the end, I'll put up the formula, but there's a formula for the difference of 2 cubes and the sum of 2 cubes.
Okay.
And we can write it all out. Right. Again, you don't need it, it just saves a little time, so I wouldn't have had to do all of this. All right, so now I'm going to look at this part. Okay, I know that x equals 1 is a root. Okay. Leave some space because we'll have a couple more. Now we have to find the roots of the quotient. Okay, because either this part could equal 0 or the other part could equal 0. Well, the other part's a quadratic. So all we have to do is use the quadratic formula, where a is 1, b is 1, and c is 1. All right? And let's see what we got. Or actually, did we already do that? I think we have the answer right here. Okay, so we already solved this equation for 0. The two roots are negative 1 plus or minus I root 3 over 2. I won't go through the whole thing again. Just go back and look at our example. So we get 3 answers. 2 imaginary, 1 real. Notice the total number of answers is 3. The highest exponent on the problem was 3. There's a connection there. Okay, any questions on how we did that one?
So if it asks for the imaginary zeros, you would just give negative 1 plus or minus I squared into the other 2.
Yep. Yep. In this case, they did want all real, right? All real zeros, or find all the zeros. So that means everything, real and imaginary. So the problem we just did, x cubed minus 1. If you bring the 1 to the other side by adding 1, you basically get x cubed equals 1. And then another way to think about solving it is to take the cube root of each side. We get x equals the cube root of 1. Okay? In that example we just did, we found all the cube roots of 1. There were 3. There were 3 cube roots to the number 1. 1, that's the easy one. And then there's 2 imaginary ones. And those are the answers we just had. So our book calls 1, you can either say 1, or you could say we found the cube roots of unity. So in general, solving, let me bring up the other problem to compare it to. If you have an equation of the form x to a power minus 1 equals 0, think about bringing that 1 to the other side and taking the nth root of each side. Think of it like that. You're finding the nth roots of 1. Okay? And how many roots you're going to have depends on the root you're finding. A square root would have 2. A cube root would have 3. A 10th root would have 10. Okay, so there are, it depends And the test will try to limit it so there's not too many to find. All right, let's look at the fourth roots of unity. So it's like you're solving this equation. X to the fourth power minus 1 equals 0. How many answers do I expect to find here? Brandon? 4. We should get 4 answers. Okay, let's factor the left-hand side. This is a difference of 2 squares. Right, so it can be factored as x squared and x squared plus 1 minus 1. That's a shortcut from Algebra 1. FOIL it and you'll see that it works. X to the fourth minus x squared plus x squared minus 1. Now, we have a difference of 2 squares again in the second part here. All right, so we could factor it more. Or at this point, we could just go right to the algebra and solve it. So either x squared plus 1 equals 0, or x squared minus 1 equals 0. Let's solve the one on the right. X squared equals 1. How would we solve this equation to get rid of that exponent? Yep. Take the square root. And what's the square root of 1?
1.
Okay, 1. Yep. What else?
Oh.
Plus or minus 1?
Plus or minus 1. So there's your 2 answers from that factor. Now let's do the other one. X squared equals, subtract 1 from each side. How do we get rid of that exponent again? Square root. Take the square root. I get x equals the square root of negative 1. And again, it's a plus or a minus. But what's the square root of negative 1? I. Plus or minus. So there are your 4 answers to all the fourth roots of 1. 1, negative 1, I, negative I. Okay, any question on that? So a couple of the facts that I'm going to write down, I've already been kind of saying as we go along. The number of answers that you've been getting has been equal to the degree of the polynomial. Okay, and the formal way to talk about these are 2 different theorems. The first one is the fundamental theorem of algebra, which says if you have a polynomial with a degree greater than 0 and you have real coefficients, then your polynomial is guaranteed to have at least 1 complex 0. And remember, when they use the word complex here, 3 is considered a complex number. Okay, 3 is a complex number. It's just a complex number with no imaginary part. Okay, but complex number is the big category that includes everything. Reals and imaginaries fall under the category of complex. Right, so if you have a polynomial with a degree n greater than 0, you're guaranteed to have at least 1 complex 0, which includes just having a real 0 as well. And the linear factorization theorem says, it's a little bit more specific. It says if you have a polynomial with a degree greater than 0, and you have real coefficients, then you're guaranteed to have exactly as many factors as the degree. So when you factor a quadratic, you factor it into 2 sets of parentheses. When you factor a cubic, you could factor it into 3 sets of parentheses. If you factor a 5th degree polynomial, it would factor into 5 sets of parentheses. So here's an example of a cubic fully factored. X cubed minus 7x minus 6 factors into x plus 1 times x plus 2 times x minus 3. Okay, I would expect that you'd be able to do something like that now. Okay? The way you'd do it is you'd use your graphing calculator and your rational root theorem, find one real root, like say -1, divide through synthetically, and you'd take this cubic equation down to or cubic expression down to a quadratic. And then from there, I'm hoping everybody could factor it. Okay, but you should be able to do something like that now, using your calculator and synthetic division. Yep.
So in order to take it down to a quadratic, you would pick one of your factors, say 2, and you would use that for synthetic.
Or -2.
Or, excuse me, -2.
Yep.
And you would use that for synthetic division, and that would be your quadratic.
Yep. Your quotient would be your quadratic, which you'd then factor. Right? The only way you'd know -2 is a root, though, is to use your rational root theorem. And then you could check it on the screen and say, oh yeah, looks like -2 is a root. And so you got to know the rational root theorem, and you got to have a graphing calculator to speed that process up a little bit. If you're missing those two things, it's going to be tough. Okay, the roots, though, they don't need to be distinct. Okay, so if you had a 5th degree polynomial, I'm not saying that all the factors and roots are distinct. There might be repeated ones, like here. Okay, we say -1 is a root, or a 0, of multiplicity 2, meaning it occurs twice. Okay, 2 is a root that occurs 3 times. So we say it's a 0 or a root of multiplicity 3. So a 5th degree polynomial could have up to 5 distinct roots, but it might only even have one root. Imagine just doing x plus 1 to the 5th power. X plus 1, x plus 1, x plus 1 5 times. Your only root would be -1 in that case. Okay, any question on that? And let's finish up with this one. So this one looks kind of hard, but it's set up so that once you find one of the roots and use synthetic division, everything factors nice. Okay, so the numbers do actually work out very nice. So I've already done part of it. I've listed all the possible values for P and Q. Remember, these are all positive and negative. So P are all the factors of 16. Q are all the factors of 3. So all my rational roots, I've listed the possibilities right here. Okay, if you graph it, it turns out that 2/3 is a root. Okay, you could confirm that just by typing it in and graphing it. Okay, 2/3 is a root. So what I'm going to do is divide through synthetically by 2/3. And luckily 2/3 is real, so we're not going to have to worry about foiling with complex numbers. Okay, so, and let's write down our coefficients. 3, -2, 6, -4, -24, and 16. Okay, bring down the 3. 2/3 times 3 is just 2. -2 plus 2 gives me 0. 0 times 2/3 is 0. 6 plus 0 gives me 6. 6 times 2 is 12, divided by 3 is 4. See how these zeros are popping up? This really helps us. -4 plus 4 is 0. 0 times 2/3 is 0. -24 plus 0 is -24. Okay, -24 times 2 is -48. And what's -48 divided by 3? -16. Okay, so I proved to you 2/3 is a root. You get remainder 0. Now, look at the quotient you're left with. 3x to the constant, linear, quadratic, cubic, quadratic. So 3x to the fourth plus 6x squared minus 24. Okay, so off to the side, we can start making our list of roots. There's more. X equals 2/3 is one of them. What can I factor out of this? Yeah,
3.
I can pull out a 3. And I'm left with x to the fourth plus 2x squared minus 8 equals 0. And it turns out this actually factors very nicely. There's x squared, okay, and we're going to need a plus and a minus, and we're going to need a 2 and a 4. Okay. Let's check it. You get negative 2x plus 4. Yep, that's good. So now when you finish solving it, you need to solve that equation. You need to solve that equation. So you're going to get x is positive or negative square root of 2. There's 2 more answers to add to that, so now we have 3. And x equals positive or negative 2i. That's the square root of negative 4, 2i. Positive and negative. So 1, 2, 3, 4, 5 answers. Okay. If you couldn't factor this, it would have been a pain. It would have been very, very difficult, if not impossible for us to do. Okay, so the homework for tonight is on 193. And it's 1 through 3, 8, 9 through 13, 15, 19 to 22, 25 to 27, 32, 36, 39, 40, and 47. Okay, so we'll go over that tomorrow, and then we'll have our test as well.